Hello people, how's it going? Welcome to the physics video lesson of the week, and today we are going to be covering the Doppler effect. Now you might have already seen the Doppler effect in another science class. You might have learned what it is or maybe where it's used, but today we're going to look at why it happens, and that's a little bit more important to me, not just saying, well, what it does, but why it does what it does. And how what we have learned about sounds and waves relates to the Doppler effect and actually gives us a real reasoning as to why it happens. And so the first thing I'm going to do with you is actually just throw a definition at you, something to write down, something to keep in mind as we move forward. So let's look at this. Bam. So the Doppler effect is an apparent change in the wavelength and frequency when a sound or a light source is moving relative to an observer. When a sound or a light source is moving relative to an observer. So, big things here. One, the Doppler effect does not happen when the observer and the source, right? The observer is the person hearing the sound or seeing the light, and the source, the thing that's giving off the light or giving off the sound, if they are stationary relative to each other, if they're not moving relative to each other, it doesn't happen. But the instant that they start moving relative to each other, either one moves at the other, one moves away from the other, or they both do that, then we start having the Doppler effect. Now, let me show you what that means, because you might be like, Mr. P, you're talking nonsense right now. So, here's just a little online simulation. It's found at this website right here, nice and easy to find. You could play around with it on your own if you want. What this is a sound source giving off waves. Now, reminder, these waves are giving off energy, not matter, right? They're not pushing the air. They are sending high pressure vibrations through the air, and they're sending it at a natural rate, a natural frequency that happens repetitively and consistently, and they are giving off these waves outwards in that circle, right? So the green thing right here, that's your observer, sound waves. Each one of these sound waves is the crest, the high point of the wave, and so if you measure the distance between two of them, you can tell me what the wavelength is. So this one is probably about, like, I don't know, it looks like about 6 units of wavelength. So all this stuff is kind of things that we've already talked about. Let's add some new things to it. Let's start moving the source closer to the observer. So now we are going to actually enact the Doppler effect. So I'm going to put the source at moving closer to the observer, and notice what is happening to the circles. They are still circles. They are not spheres. They are not ellipses. But because the observer is almost chasing after that sound wave, almost following it in that direction, the circles are closer together on one side and further apart on the other, which means that if we were to pause it right here, the observer is now not experiencing that same sound that he experienced when the source was stationary. The observer is now experiencing a much shorter wavelength, and if they have a shorter wavelength, they're also having a lower frequency, right? They're getting, or sorry, a higher frequency. I'm sorry, the two are inversely related. A shorter wavelength means a higher frequency. They're getting hit with more waves per second now than they were when the observer was stationary. So right now they're getting hit with a wave, bam, 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 bam. But now if I move the source forward, they're going to start getting hit with waves at a higher frequency. That higher frequency relates to pitch. A higher frequency relates to pitch. Pitch and frequency are one and the same in terms of sound. So right now, the observer will hear a higher pitch, but then once the source moves away, here let's move this guy a little bit closer, once the source starts moving away, notice that the observer experiences a lower frequency. They get hit with less waves per second and a longer wavelength because now the observer is moving away. And so that's where you get that train whistle that does the eew, right? The that's the higher frequency. That's when it's moving towards you, and the ew is the lower frequency when it's moving away from you. Now we can experience the same exact thing. Let's put that stationary, and let's move this guy back. But we can experience the same thing if we just move the observer towards him. So now if the source is stationary, the observer is still experiencing a higher frequency in this point and a lower frequency in this point. So now they would experience the exact same thing, that as it goes past. Okay? And so that is where, whoops, we have this right here. The apparent change in wavelength and frequency when a sound or a light source is moving relative to an observer. So when the observer or source are moving towards each other, the observer perceives a higher frequency or a higher pitch, and when the observer and the source are moving away from each other, the observer experiences a lower frequency or a lower pitch. Okay? This relates to my original image, wha-bam, quite well. Now I asked you at the start of the week two things. One, what took this picture, and two, what are all the dots? So let me give you those answers. The thing that took this picture is the Hubble telescope. Now the Hubble telescope is pretty interesting, and it's also something that I realized students don't realize a lot. The Hubble telescope is in outer space. It orbits us, and there's a reason why. There's a reason why we don't see this in our night sky when we look up, and it's because we have an atmosphere around us. The atmosphere does a really good job at protecting us from really high energy light that wouldn't be good for us, right? We use sunscreen to protect us from UV rays, but people don't realize that, well, we also use the atmosphere to protect us quite a lot from this as well. And so the Hubble telescope said, I don't want, well, it didn't say anything, but the people who designed the Hubble telescope said, I don't want these light sources being blocked. Let's put it into outer space where it can get all of the light sources without the atmosphere blocking it. So it puts it out into outer space, and this image is unreal to me because it is an image of all these dots being galaxies. Every single one of these dots is a galaxy, and every single one of these galaxies could have thousands or more stars in them. Maybe, who knows, maybe these stars also have planets orbiting them as well. We have no idea. The amount of stars, the amount of planets that you could be seeing in this picture behind me is unreal. It's mind-boggling. It's phenomenal, really. It's something that I can't even explain. And the harder part about this is that the percentage of the night sky that this is looking at, this isn't the entire night sky. This is such a small percentage of the night sky that it is about the size. If you were to take a dime, hold it at arm's length away, it would be the eyeball inside of the eye of the dime. That's how big in the night sky. So it's like a little pinpoint of the night sky, and yet we have this many galaxies in it. It's kind of ridiculous. Now the reason why this is interesting is because of what we call the redshift. Now light, just like sound, has wavelength and frequency. I'm going to do this really quickly. You don't necessarily need to know this for the regents, but it's just something that I find that I think students need to know if they get through a first year physics course. Light has wavelengths relating to color, whereas sound has wavelengths and frequency relating to its pitch. And so the longer the wavelength, the more red the light, right? We have our Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Violet being the shortest wavelength, the highest frequency, and red being the longest wavelength, the lowest frequency. Now, when we started looking at all of these stars, we started to realize that their colors were more red than they should have been. Based off of their temperatures, they were more red than they should have been. And this confused physicists and scientists for quite a while, until we started to realize that every single star was red, getting more and more red. And what does that tell you? Based off of our Doppler effect, because they are more red, they have a lower frequency, which means they are moving away from us. And it was one of the first big pieces of evidence to show us that our universe is expanding. And it's expanding at a kind of alarming rate almost. One that we can't necessarily describe or really know the true details as to why just yet. But it is. And so this idea that this red shift, the stars being more red than they should be, is evidence that our universe is expanding. It's kind of interesting, all based off of our Doppler effect. Alrighty, that is it for the lesson today. You will have a flipping physics that goes through kind of the same stuff and touches upon maybe things that I missed out on. And yeah, see you later.